Thank you for joining us for the HPL seminar today. With all the hellos and hugs and everything I've seen today, I don't even know if I need to introduce our speaker, but I will still do that. So it is my pleasure to introduce our speaker today, Dr. Michael Slawinski, a professor at Memorial University. Dr. Slawinski earned his PhD in mathematical modeling, actually here from the University of Calgary, in 1996 under the supervision of Dr. Brown. For most of his academic career, he worked in the field of continuum mechanics, in which he made contributions to coordinate-free inverse problems within the scope of material symmetries. And more recently, he's been applying his expertise to competitive cycling, optimizing performance under various constraints. In addition to his academic work, Dr. Slawinski has an impressive athletic background. He has competed in cycling and cross-country skiing, and he's consulted for the Ineos cycling team on 2 successful hour record attempts, including their most recent record in 2022. Today, he will be presenting his talk titled On Minimizing Ascent Time and Maximizing Ascent Speed in Cycling. Thank you.
Thank you very much. I guess I'm supposed to turn on this. Is that true? I am turning this on.
The switch right between the things.
The switch is right here.
Yeah.
Great. Can you hear me now better? Very good. Thank you very much. It's fun to be here. I was here last time in spring 2023. So I'm returning after a few years. So it's always fun to be back. And the title of the talk, as you can see here, is sort of you should be questioning when you see this title on minimizing ascent time and maximizing ascent speed. Should be the same thing, right? If you maximize the speed, you optimize the time. Well, it's perhaps written like that to provoke a thought. Minimizing time is when you are given an uphill and you try to set up the best system for climbing that uphill that's already set. For instance, for us here in Calgary, would be say you'll be going up the home road and you want to maximize and you want to minimize your time going up home road. Maximizing the ascent speed is something else. It's something that we associate with VAM, the way you are trying to find what could be the fastest way for you to gain speed. And that depends, you are free to find an uphill in which you'll be gaining the height in the fastest possible way. So for some of us, it will be, say, an uphill of 10%, 7, 9, 11. For some people who will be climbers, will be something 25%. So that's what you're trying to optimize, finding a good uphill along which you can be maximizing the ascent speed in a sense of the vertical component of it. But so that's what just about the title, because the title itself is already a number of questions. And let me go to the next slide if I can now find how to do it. Here we are. One of the things that we have to think about is how, when you have a situation when you are racing, especially a time trial. So my talk now is going to be about the time trials, meaning you are alone on the road. You don't have any riders with you. So you cannot be drafting. You cannot be optimizing your situation with a draft and trying to hide behind the rider to be less tired at the end of the ride, at the end of the race, etc. You are alone. But you can still have a variety of options that you can follow. For instance, it's very common to have a time trial when you have a flat race at the beginning and then you have an uphill. And now it is allowed to change your bicycle, which of course takes some time. You have to stop, change the bicycle, and then try to climb. Why would you do that? Because you will use a different bicycle for the flat with a different setup of ergonomics in particular, and a different bike for climb, where ergonomics is not so important because the resistance of the air is going to be proportional to the square of the speed. So you are moving much more slowly, but you want your bike to be light. So you can see here, I pointed out, we have Lagrange trying to optimize the situation of going on a bicycle that's very ergonomic, and then Newton is going up the hill on a bicycle that's light. Should you or should you not change the bicycle? It depends on how you ride, depends on the uphill, its length, its steepness, etc. And how important it is? Well, some of us might remember that Giro d'Italia in 2023, which is 21 stages, at the 20th stage, the leader was Geraint Thomas, a fellow from Wales. And he was winning by about half a minute over Primoz Roglic. And then this final time trial. What can happen? What happened in this case, that Roglic made a strategy better about the switching of the bicycle and ended up winning by 14 seconds. He won Giro d'Italia of 3,448 kilometers by 14 seconds because of the proper formulation of what to do on the stage that was only 12 or 15 kilometers. It was 13 and a half, but that's not what's so important. Aerodynamics, something that people did pay attention before, much less that they are paying attention now. Let's take a look at another point of history. And to move it to the next thing, I press here. Well, many of you were not born here in 1989 when there was the last stage of Greg LeMond and Laurent Fignon. And it was the very last stage. And Laurent Fignon was winning by 50 seconds. It was a fairly short stage, 24 and a half kilometers. That's it. So almost no way you can pick up 50 seconds. But Fignon, sure, had his skills. At the same time, to show his ponytail, he decided not to have a helmet, in contrast to Greg LeMond, and you see with the helmet, the aerodynamic no helmet. And something that was very new in cycling at the time, he used the tri-bars. Actually, we call them the tri-bars because they came to cycling from triathlon. They were allowed in triathlon, but they just became allowed in cycling. But of course, when Greg LeMond won the race, people started to say, no, he shouldn't have used that. But he was okay with the rule. So he still won by 8 seconds. The entire race of 3,285 kilometers won by 8 seconds. I had the pleasure of meeting the late Fignon. He died quite young, at the age of 50, died of cancer. By the way, he wrote a very beautiful book. He was a very bright fellow. If you are interested in a book that sort of gives a perspective of cycling and the life they had, the title is When We Were Young and Careless, by Fignon. Comme nous étions jeunes et insouciants is the French title, the original title. And I had the pleasure of speaking to Fignon, and he was telling me that, one of the annoyances in life, I won Tour de France twice. Once, actually, he won when he was only 21 on his very first attempt of Tour de France. It's very common that people say, okay, the first time I raced Tour de France, I just race to see how it goes, to get familiar with it, to get some experience, and then I'll maybe try to win it. He won it on his very first attempt, and then he won it again. But whenever people would see him, they would say, you are the guy who lost Tour de France by 8 seconds. So, sometimes it's better to win than to lose more of the time. And if you want to lose, try not to lose by 8 seconds only. One of the things that is very important in cycling now for the last about 30 years is power meters. Power meters change the way we approach cycling from the coaching point of view, from the strategizing point of view. And Greg LeMond, whom you saw a moment ago actually, said in an interview that if he could have had them, he would have maybe stayed and competed for a couple more years. He retired because he felt it was time to retire. But this would have perhaps kept him for a couple more years of competition. What's power? Power is a moment of physics, is work divided by time, which means how quickly it allows you to do certain amount of work. Because let's remember from our physics classes, which you should all have studied very deeply, and if not, make sure you go back and study. The work is going to be the same regardless of the speed, because the work is a difference in potential, which means that if I walk up, or let's go back, let's go back to maybe the home road. Do you remember the home road? The home road, do you know it? Do you cycle up home road? No. Well, try it next time. And the work you do is going to be the same regardless of the speed. You take a minute and a half or a couple of minutes to do it, or you take 20 seconds to do it. The work that you put in is going to be the same. What's going to be different is going to be the power. Because the faster you do it, work divided by time, the faster you do it, the greater the power you have to put in to go up the hill. That's good theoretically speaking, but how do you measure it on a bicycle? You cannot just measure time, you cannot go up and measure the time, measure the work, and then divide it, and so on. How do we do it on a bicycle? Well, another important thing in science is to know the units. The very same units that you would get of work over time, which would be the watts, you would get if you were to multiply force by speed. With speed? Speed of the rotation of the pedals. So force is the force of pressure that you put on the pedals, and V is the speed of the rotation of the pedal. Not the speed, not the rotational speed, but the linear speed of the pedal going around the circumference. That's why, for those of us here who cycle and who have power meters, they always ask us the size of the crank that we have, because the crank is changing the length of the motion of the pedal over one revolution. So that's how something that theoretically you say, work over time. How can I measure that if I have an instantaneous measurement that I need? Well, look at your bicycle. You can do it just in a bicycle by measuring the force and multiply, and then of course measuring the speed of rotation and multiplying them by each other. And that's an Italian company that is producing very nice power meters, and they sponsor some of my research. They are very, very good in that. And you can see here, those are the measurement of the pressure, piezoelectric structure. And then, of course, you have a gyroscopic structure to measure the speed of the rotation, or the speed, the way it moves, not rotationally, but along the circumference. The other way. Here we go, just a little bit of math. The way we do our power is that power will be here formulated in a model. You have to come up with a model. The model that we are doing are going to be phenomenological models. What does it mean, a phenomenological model? It means the model in which you decide to put into the model what you think is important. It comes from philosophical concept of Husserl, who was a phenomenologist from a philosophical point of view. And the idea is we are seeing and perceiving things the way they are, the way we interpret them in the first view or person that we are. Which means I am not looking at the fundamentals of science. I am looking at what I think is important to put into the model. Most models that we do like that, are done in the same manner. Which means that you decide, for instance, what would be important? I guess air resistance. Let's put it in. What else? The resistance of the rolling of the tires, and so on and so on. The inclination, of course. Then you decide if it's good or not. How do you decide? By empirical evidence. You decide by testing. You decide by seeing if that makes sense because it agrees with the measurements. This is very different, for instance, from fundamental studies. You might know it. I did my degree in physics, so I have all those physics thoughts about it. When Eddington went to a nice island close to Africa to make measurements of bending of the light rays, during an eclipse to see if what Einstein thought that the light ray would bend in the gravitational field was true or not. The story is that when he came back to talk about it, then Einstein was not that interested in hearing anything about it. And one can view it as Einstein being arrogant, which I don't think he was. But he really didn't have to check that because theory of relativity was a fundamental theory, was a theory based on fundamental concepts of physics. If this was not true, that would mean that basically all of physics fails. We are wrong. We are wrong about our mechanics. We are wrong about our calculations. We are wrong about our assumptions. It's all wrong. Very unlikely. So that's why it's sort of a story to show the emphasis that phenomenological model, which is almost all the models we do, is different from a fundamental model, and as such needs a verification from an empirical point of view. We actually use a term, philosophers of science use a term often, that we must make sure our model is empirically adequate. That as far as our observations go, they agree with our predictions. So they're empirically adequate. So what do we do here? We have basically the following things. Power, in the numerator, I have the kinetic power due to kinetic motion, and then power due to resistance of other forces. So we have here, right here, the first one would be the change in speed. The second would include also this change of elevation. The other ones would be the resistance of rolling, the air resistance, and the efficiency of a drivetrain, which means that would be your lambda, which would be how efficient is your bicycle. If lambda is 0, so you're just dividing by 1, meaning nothing changes, then it means very efficient or impossibly efficient. No bicycle, no machine can be efficient up to 100%. So it's generally something very small, if you have a well set up bike, about 1%, maybe 2%, depends also on kind of a bike. By the way, the reason, for instance, there's a statement for my truck friends, as you probably know, the bicycles on the velodrome have a fixed gear. The fixed gear means you cannot stop to pedal, you cannot pedal backwards, and as the bicycle goes forward, you can see the pedals moving, as opposed to a free wheel that we have on most bicycles that we use. One of the reasons, perhaps the main reason to use the fixed wheel is that it transmits the power better. If you have a free wheel, you might be losing 1% or so of your power in transmission between your legs, your pedals, and the wheels. If you have a fixed gear, you don't have that loss. So that's another reason to use the fixed gear. So here it is. Here is our phenomenological model that we are going to be using. Notice another thing. You want your model, that's again a statement of Einstein, supposedly, that you want your theory to be as simple as theory model, as simple as possible, but not simpler. So here you see that our formulation, our model, has 3 parameters. It's a 3-parameter model. The parameters are the coefficient of resistance. I will go back, which is here. Yes. The coefficient of resistance of rolling, the coefficients, your CDA, which means how much your air resistance, how big you are, how bulky you are, how well positioned you are, the coefficient of the resistance of the air, and lambda, the coefficient of the drivetrain. So it's a 3-parameter model, which in a way is a very simple model, and you want it to be as simple as possible, but not simpler, in order to be able to look at things, to model things, to modify things, to understand things. If you make a model that has too many parameters, sure, the model can even potentially be more accurate, but you pay a big price for this extra accuracy of the model. Imagine, for instance, when you have all done that, for instance, you have the points, which you plot, you make some measurements, and you plot a series of points, 20 points or so. What should you do now? You want to connect those points. Should you connect those points in that manner, that sort of point to point, which would be very accurate in a sense that there's no error between measurement and your regressional analysis? You probably will do it. You will try to fit a straight line into it. You will try to fit a parabola or some other, maybe sinusoid. You will not try to fit every point. So it's the same spirit. You want your model to be relatively simple in order not to make it such that it's really awkward to maneuver with this model, to play with this model. And I go here, okay. Here I wanted to show you the model that we just talked about a moment ago is here. Just for comparison, I think that's a very interesting slide that you would appreciate. Here is what I was presenting to you in 2023 when I was here in the spring. I was talking about the velodrome. I was talking about the hour record. I was talking about modeling for the velodrome. Notice some of the differences. I'm not going to go through details. If you like, you can always talk about it afterwards. You can get in touch with me. I'm still in Calgary for another 10 days. We can look at the details. But I just wanted to tell one difference between the two models. Here, in this model that we saw on the previous slide, we have V, which is the speed velocity of the center of mass of the bicycle going up the hill or going on the straight, on the flat portion of the course. Here, notice, we have capital V, which is also the speed of the center of mass, and a small v, which is the translational speed of the wheels. Why? Well, on a velodrome, especially for, say, Filippo Ganna, who is taller than I am, he's 193, when he was setting the hour record with a speed of about 57 kilometers an hour, he was leaning on the velodrome by very, very much. So that means that his wheels were following a trajectory different than his center of mass. Because of the leaning, you can see that he was leaning and say the wheels are going along the velodrome here. Center of mass is inside the velodrome. So the speed of movement of the center of mass is different from the speed of movement of the wheels, translational speed of the wheels. I'm not talking about the rotational of the wheels, just a translational of the wheels. So we had to make a difference between those two because of the peculiarity of a velodrome. The velodrome is 250 meters, so it's less than a running track. So you really are leaning a lot for a good portion of the ride, which means that you have to distinguish them. Here we don't. You can see this phenomenological structure of the model. Would it be important for an uphill to distinguish between the translational speed of the wheel and the center of mass? Probably not. Let's not include it. On the velodrome, yeah, considering the leaning that you do about 50 degrees, you definitely should make a distinction between those two. So that was the point of an illustration of those two things. Now, if you want to look at the details of it, those details are in the papers that we published, and those papers are online, and I am not going to go through the details. The papers are quite mathematical in a sense that all the people here, the authors are mathematician physicists. So we approach it from a mathematical point of view. I should maybe say that right away because we are in the laboratory where a lot of you are dealing with the physiological questions. There are no physiological questions that we would ask ourselves. Somebody would say, what would be the speed necessary or the power necessary to climb that hill at such and such a speed? We do those calculations. Somebody would say, but that's physiologically impossible. That's not something that we would look into. That's something for a physiologist to look into. So a good collaboration would require a combination of physiologists and math physicists who would sort of look at those two things. So here's a couple of things that I would like to read. It's probably too small for you to see, so I'll do it. The abstract of this first paper, part one, we start by saying, we proved that given an average power, the ascent time is minimized if a cyclist maintains a constant ground speed regardless of the slope. So there's of course a constraint here. The constraint would be, what is your average power? What average power can you maintain on home road? For 400 watts, 600 watts, what would be your average power? So we proved that under the constraint of the average power, the ascent time is minimized if a cyclist maintains a constant ground speed regardless of the slope. There's an interesting point. You might have a slope that, of course, as mathematicians, we always would have some sort of a constraint. We assume that there are no flats on this uphill and there are no descents. So it's a monotonic increase, mathematically speaking. But even though it undulates, you would optimize, you would minimize your ascent time if you maintain a constant speed. Herein minimizing the time is equivalent to maximizing for a given uphill, an important point, for a given uphill, the corresponding mean ascent velocity, VAM. When you see those of you who cycle, or even if you run up the hill, you might see on your computer, on your Garmin, something saying VAM. That means how many meters or how many kilometers, generally meters, you go up. What's your vertical speed? And the vertical speed can be, if you're very good on a bike, about 2 kilometers an hour. You can gain an increase in elevation of about 2 kilometers in 1 hour. That would be the top guys. And it's commonly called VAM, even though many people might not know it, is coming from velocità ascensionale media, the medium ascent velocity. And it was created by a physiologist, by a medical doctor, Michele Ferrari. He was the one who started to do it, and he would measure for the guys, for the cyclists, what's your VAM? And so how good you are in gaining height as you are climbing. And then there's a part two, the very same authors, which we sort of extended some of the things. I'm not going to talk to you about the details, but if you want, those are very accessible. We have them put on archive. So you probably all know archive, the system of archive on the internet. You just go on archive and you put the names and it'll come up. You don't have to subscribe to any journal. It's a public domain. And so all those things are archived. Notice what I wrote here that was of an emphasis here, maximizing ascent time, given an uphill. Choosing an uphill that fits best your structure, your size, your weight, your style of riding. The uphill is already given. Let's proceed. So what we are basically trying to find out, that's where we are heading with that. We are trying to find out, should I, if I have the flat followed by the uphill, like the Giro d'Italia that Primoz won against Geraint Thomas, should I change my bike or should I not change my bike? Should I stop and change my bike, or I would lose or gain by changing the bike? So that's why we are asking ourselves those questions. Standing, start, which means I stop and change the bike. And what is the situation? Well, we assume that the average power, the numbers were just written like, we just chose those numbers because they were convenient to show, but there's nothing amazing about we can change the numbers. We have all programs. Am I disconnected? I somehow hear it differently.
Is the battery still?
The battery has died. Or maybe this got. Yeah, probably the battery has died. Should I speak loudly?
For now.
Great, I'll just speak more loudly. So here we have just to give you an idea, we just make a model. We have those algorithms, we wrote the code. Actually, one of the four authors, who was going to be a postdoctoral fellow in the department, but decided to do something else, unfortunately for me. And he did a lot of those models as far as the coding. They were all done in MATLAB. So it's nothing amazing in a sense that they were just mathematically solving all the problems, optimization concepts in MATLAB. And so the model here that we are looking at is the following. We have a mass of 70 kilograms. There's the cyclist together with the bicycle. Ah, wonderful. We are set. So I am putting this back and this back. Yeah, I can hear my own voice. Mass 70 kilograms, the gravitational acceleration, rho, density of the air. For instance, the thickness of the air is extremely important. When we were in Switzerland for the hour record, we were hoping for the rain. We were hoping for light pressure. This would make a difference of, let's say, about a kilometer of an hour record, because the hour record is how many kilometers can you cover on a velodrome in 1 hour. You start, you go for an hour, and how many kilometers can you cover? And the record now is almost 57 kilometers in 1 hour. So if the air pressure is low, then the difference could be of about 1 kilometer. So here you can see how that's an important parameter to include the density of the, the density of the air. This, by the way, the key reason perhaps that we didn't have it as a public event where people could go and buy tickets and then come in and watch it. There were a couple of days given for it in case it turned out to be a very high pressure day. And then, well, it's a show. Tickets are sold, people are there, so the rider needs to ride. No, the idea was that if necessary, the rider can decide, let's ride it next day. Let's maybe take a couple of days until the pressure becomes a bit lower. The density of the air becomes a bit less. CDA, we took here 0.3, it's quite high. CRR, lambda, 2%. So the loss of power of your bicycle is about 2%. And the speed that you would end up getting is about 4 kilometers. So that will be the speed that you will be moving. So you are here starting, you are accelerating, and then you are proceeding at a constant speed, because that's the best way to proceed on the uphill. Notice that we also put a maximum speed, the idea being that you don't want to blow up. You don't want to start in a manner that you start like crazy, and then sure you gain a fast speed rapidly, but then you are gone, you are burned. So that would be a standing start. Now, launch start, the very same power, the same maximum power. So we are starting with a launch start. So you are going on the flat, and you are carrying on that speed up the hill. So that means that you are starting your speed not at 0. You might have seen that on the previous slide, you have the initial velocity 0, because it was standing start. In this case, we have initial velocity of almost 12 meters a second. Of course, once you start the uphill is quite steep. You start this uphill, so starting the uphill, you are losing speed, and then you're carrying on the speed of about 4 kilometers per hour for the entire time. Which one is better? It depends. I'll show you in a moment. It depends how long is the uphill, for instance. That's one of how steep is the uphill. Let's proceed to the next one. So here it's a question to change or not to change. That is the question. And the initial launch, we have like that, and we end up with a speed of 3 up. Here we go back. The initial launch was here. Why is it faster than before? Because you decided to use a time trialing bicycle, the one with aerodynamic position, the one with disc wheels. For instance, you would not use the disc wheels on the uphill. Disc wheels are great from the point of view of air resistance, but they're heavier than spoke wheels. So if you're going up the hill where you're not moving very fast, so the aerodynamics is not so important. You have spoked wheels, not disc wheels. But if you're just using it on the flat, then you'll be using the disc wheels. So there's a greater speed here, sorry, greater mass, and then greater launch speed. So that's the initial launch. Then if you don't change it, you are continuing with the same length. The resistance will increase from 0.2 to 0.3. Why? Because from the position on the time trialing bike on the flat, when you are extended in that manner, you are getting up and you are riding that way up the hill. You are not riding up the hill in that position. That wouldn't be convenient. That wouldn't be comfortable for you to do that. So your CDA, the coefficient of drag, that's where CD is coming from, the coefficient of drag is increasing from 0.2 to 0.3. And that was your initial speed. Here, if you do change, you get a lighter bicycle. That's the main difference. The initial speed is 0. And then your CDA was the same as here because you are basically riding on the hoods of the bicycle, on the hoods of the brakes in a manner that you are sitting in a not ideal position from the point of view of aerodynamics, but better from the physiological point of view. You can breathe better, you can perform better, even though it's not best from the physical point of view, from the aerodynamic structure. Here it is. To change or not to change? This is the question. This is the setup that we have here. The diagram shows here. Here's the time. Here's the distance traveled, the distance of the hill. And here is on the lower one, the time is going to be shorter, a little bit shorter, but as you could see before from the picture we have of Laurent Fignon and Greg LeMond and Primoz Roglic and Geraint Thomas, that a little bit makes a difference of you winning or not winning Tour de France or Giro d'Italia. So here you can see that up to a certain point, it's better not to change. From some point on, it's better to change. This intersection point is precisely the point when you should be changing. So, for the cycles that we had before, 70 kilograms, 68 kilograms, etc., of course, it will change with every cyclist. Somebody cannot ask, if a coach will come to me and ask me, so should people be changing or not changing? It depends what are the conditions on the road, how steep is the uphill, how long is the uphill, who is the rider, but we just put the parameters into the model, and then we can try to estimate it in a reasonable manner. So on a 10% uphill, you wouldn't change the bicycle unless it's longer than, say, 2,700 meters. If the uphill is longer than 207,000 meters, 2,700 meters, then you change. On a 20% uphill, which is steeper, of course, you will change much more rapidly. You change about a kilometer and a half, 40, 54. Calculations one has to know that we do those calculations, and then we follow up to 4 decimal points because we are mathematically putting things like that to be able to make sure that our model is correct from the point of view internal structure. But of course, if you are talking to a coach, you will not say 1,454 meters, 0.1236. You say, well, if the uphill is longer than 1.5 kilometers, then consider changing the bicycle. If the uphill is shorter than 1.5 kilometers, then it's probably not worth it. So that's how you would address that thing. We are not that far from being done. We are on the slide 11 out of 17. So let's proceed. Here we go to the next one. So now we are switching to this other part of the title. The uphills to maximize ascent speed. What uphill should I choose to maximize the ascent speed? Let's say that we are here among ourselves, we decide to find out who would have the best van. Which means that you would want to calculate how quickly you make a vertical ascent. Some of us, the lighter people, might say, I will choose a very steep uphill, and that's what will give me the advantage because of my body build. Somebody who is bigger and heavier would say, I cannot go for such a steep uphill, so I'll try to maximize my van, get the fastest vertical component of my speed by going on a slightly less steep hill. For instance, I will not talk about that, but nowadays there is a new sport in a way, which is called Mount Everesting. When you are Everesting, trying to see how quickly you can gain the ascent distance, ascent height of Mount Everest. Cycling. I mean, it has nothing to do with Everest in a sense. You are not going to the Himalayas. You are just finding, say, home road and go up and down home road until you get 8,848 meters of elevation gain. What hill should you use for it? How steep should be the hill that you would use for it? If you Google Everesting, you will see there are people who really have some nice results and they devote their lives to Everest. So here, what we are saying here, I'll just read the first sentence perhaps. Maybe let's say the title first. On the brachistochrone problem for cycling ascent. Brachistochrone problem, for those of you who are not from mathematics or physics, was a very famous problem that was proposed by Bernoulli, who was a mathematical physicist in Switzerland, and even though the last name is Italian, and the point was the following: what trajectory would you choose if you wanted to go from point A to B in the shortest possible time by sliding? So say, what would be the slide that you would build to get from A to B in the shortest possible time? Brachistochrone from Greek is brachisto, shortest, and chron, time, shortest time. So of course, shortest distance would be, let's make a straight line from A to B. But if you make a straight line, there's the shortest distance, but not necessarily the fastest. You would maybe want to start to quite a bit more steeply to gain speed, and then turn in such a manner that you get to point B, sort of on a flattish way. Again, you don't want to do it too much, because sure, you gain more speed if you go near vertically, but then you have a lot of flat to go. This is a very difficult problem. The solution of it was the cycloid, but an interesting thing that it led to the creation of a new branch of mathematics called the calculus of variations. And my research group that I directed for a quarter of a century, because really I'm retired now. I'm happily, retired. So I am still officially at Memorial University, but I'm a professor emeritus. So I'm happily retired. So I led this group for a quarter of a century, and it's right here. Do you see that? For those of you mathematically inclined, it is a variation of the integral of the Lagrangian equal to 0. That was created, the image was created by a friend of mine who is not here today. He was going to come. He was one of the designers of IKEA. So he designed beautiful IKEA things, but perhaps the most important thing that he did in his life was designing the logo of the calculus of variations for my research group. That's what the brachistochrone is. So on the brachistochrone problem for cycling ascents, if we are going to descend on a bicycle, we would choose something of that sort. But what would be the best uphill that we want to climb depending on our body build and our structure? So the abstract starts saying that VAM, velocità ascensionale media, is a measurement that quantifies a cyclist's climbing ability. We show that to minimize the time to attain a given height, which is tantamount to maximizing VAM, a cyclist should climb as steep a constant grade hill as possible. The limit of steepness is imposed, among others, by such factors as the efficiency of pedaling, which is related, among others, to the visibility of cadence, maintaining balance, preventing skidding of the rear wheel, etc. Starts to be complicated because abstracts are very concise, sometimes too concise to understand. So we have 5 more slides to explain that. And here we go. What do we have here? What do we have here in the following? Very simple graph. So I know it's been already 45 minutes, but we are done in about 10. So just pay attention, please, for the last 10 minutes. Power 300 watts, mass 68 kilograms, And here we have a steepness. Here we go. I went back. And here we have a steepness of the climb, 5 degrees up to 20 degrees. Very simple. What you have here is the speed of ascent, but the speed of you, meaning not the vertical speed, but the speed with which bicycle moves, the ground speed, if you wish. Makes perfect sense, right? If you are at 20 degrees, then your speed is about 1.2 meters per second. If you are at 5 degrees, your speed is about 4.5 meters per second with a power of 300 watts and your weight together with the bicycle of 68 kilos. A very light rider, obviously. The next slide is this. It's something extremely interesting. So I would like you to sort of, focus on it because it's something really, really beautiful. Here you have the same horizontal axis, which means 5 degrees inclination, 20 degrees inclination, and here the same power, and that's the vertical component of speed. The vertical component of speed, which means the ascent speed, the speed how quickly you gain altitude. Notice it's increasing. The steeper the uphill, the more it's increasing. Of course, it's from 0.4 from 0.39 to 0.43. The difference is not very large, but you basically should try to go as steep of a climb as you can. Because although your ground speed would be diminishing, your vertical speed, the vertical component of that speed, will be increasing. More and more, the power will be given to your vertical component of speed, to gaining elevation. This is, in a way, when one sees that, this sort of beautiful things in mathematics, one should have some tears in one's eyes, seeing it's so beautiful, if I don't have tears in my eyes when I see beauty of mathematics, that would mean I have no soul. But since we all have soul, probably all of us have a bit of a tear in our eyes, seeing the beauty of what mathematics is telling us. So I'm repeating it again, almost like an encore in an opera, that the steeper the uphill, the greater is the vertical speed. The vertical speed of ascent, or what the vertical speed is, obviously the speed of ascent, becomes greater the steeper the uphill. So now is the time, for instance, that you would want to climb 1,000 meters, meaning the vertical distance would be 1,000 meters, which is a lot for some of us. Although, some of the races, for instance, when you see the race, the world championship that were in Africa this year, during the race, they were doing over 5,000 meters elevation gain. So that's quite a bit. But when I cycle in the Dolomites, and I know that I have a pass of 1,000 meters to do, that it's enough to intimidate me. So I just chose here that our altitude difference is to be 1,000 meters. And then I can choose to climb this 1,000 meters on a variety of uphills. I can look for an uphill, if I can, that would have a 5% incline. So it would be a rather steady, longish uphill of a 5% incline. Or I can find on the other extreme one that would have a 20% incline. So I would do the 1,000 meters elevation gain with a 20% incline. Look at the time. The time that would take me to do that with 300 watts on a 5% incline would be 2,542 seconds. We can convert it to minutes, whatever that would be in minutes. And if I go to do it on the 20-degree uphill, then it will take me only 2,303 seconds. So I'm better off trying to choose the steepest uphill that I can. Well, in a way, I can tell you that when I started to do that study, I was expecting some kind of a local minimum or local maximum. I was expecting that my answer would be, here it is. I was not expecting that will be just going up and up and up, and basically telling you, choose the steepest uphill that you can possibly climb. So that's almost the last two slides when we'll be answering. In science, we often don't answer a question, we just ask more different questions, and then we pass to the other things. It's not so much the answer itself that we get. Conclusion. Given started endpoints, as well as a fixed average power, the brachistochrone, in this case, the trajectory of the fastest ascent, is the straight line. Valve is maximized by the shortest distance covered with a constant speed, which implies the steepest possible constant grade hill. Notice this that what follows, you are often told when you are studying that you are supposed to write discussions and conclusions, right? Because it's implying that you discuss and then you conclude. But I think what happens often that you conclude and then you discuss, because you made some conclusion, but conclusions are never certain. So you always have to discuss your conclusions. You have to say what's weak about them, what is the reason that we should proceed with that study or do some more experiments or more mathematical modeling. So that's why the next slide, the very last slide, is discussion. What should we do? What should be? Here you see from our 5 degrees to 20, the thing says, the steeper the uphill, the faster your vertical speed. The steeper the uphill, the shortest your ascent time. Well, talking to some coaches in Italy, they suggested that perhaps around 12 degrees would be for many cyclists, not all, for many would be a reasonable value, which in cycling we tend to use the percentages more than degrees. So for the percentages, that would be about 21%. And so that would be happening somewhere around 12 degrees, would be around here, which sort of makes sense in a sense when you look at the graph that you start to lose here. There's a big difference in the first maybe 10 degrees. There's a big difference between time that you get at 5 and the time that you get at 10. Then it becomes less. So you're going to a steeper and steeper hill. It's going to be more awkward to ride, even from the point of view of balance and speed, but you might at the same time gain very little. So, sort of in economics, the rule of diminishing returns, there will be something of that type. So the coaches did suggest that about 21%, which would give a speed of about 2 meters per second, that's your speed with which you are moving, the ground speed. Which is about 7 kilometers an hour. Going less than 7 kilometers an hour on a bike becomes awkward. Going very slowly, you start to, for instance, I remember in the Dolomites doing some of the uphills that were so steep that you would be pulling on the handlebars and you would have your front wheel basically just lifting from you pulling on the handlebars. They were so steep. And also there's another thing, when you were to get up, for instance, your rear wheel would start to skid. So there's a number of things. That's why in the case of our work here, this is part of the work of being good in doing those strategies. There has to be experimental study when, depending on the rider, some riders might be comfortable on that steepness, some might not. Their style of cycling might be such that they are not very good in keeping the rear wheel without skidding, or the balance, they might find that if they go below certain speed, then they find their balance very awkward. So all those things are to be taken into account. So the speed about 2 meters per second, which is about 7 kilometers an hour, we thought was reasonable. The next thing, the RPM, your cadence, how fast you are going to be moving your pedals. So that of course depends on the gears you have. Gears that are not very uncommon would be 36, 32. So you would have the main you would have the front piece at 36, the cogs at 32, which is not an unreasonable thing to have. And in this case, the calculation that we made with the bicycle was the circumference of the wheel, etc., that will correspond to about 50 RPMs. So the cadence of about 50 RPMs, which again, if you start to go below 50 RPMs, if you start to pedal in a way, that's not an optimal way of pedaling. You might not want to go for the cadence of 70 or 80, which might be in many cases nicely. You are going down to 50, so less than one revolution a minute, one revolution a second, but still not that awkward, not that uncomfortable. So here it is. We are finishing that with the discussion as opposed to finishing with the conclusion, because one can take this mathematical modeling from the physics point of view and now engage in a physiological point of view and engage in the way that a given cyclist would like to do it if he or she wanted to maximize their VAM or on a given uphill minimize the ascent time. Thank you very much.
The floor is open for questions. Who would like to start us off? Brent.
Thank you for that. Can you talk about the critical elements in the model when you wanted to make it specific to an athlete? So you're using 300 watts
Yeah.
for the model to drive the model. Do you get sort of an understanding of the average power output an athlete can have? Is it critical that you know things about their stature, their surface area that impact the?
Very much so.
So what are the critical kind of things that you can?
This is a very much critical thing. So for instance, from the point of view of CDA, we will do a lot of measurements. We will do measurements while cycling, which are very important, the dynamic ones. We also would use the wind tunnel. There's actually a nice wind tunnel at Politecnico di Milano, where one can do the measurements, and that's actually where some of the teams would come to do the measurements in the wind tunnel. But one has to be careful because all the information you get is never conclusive. You always should say, but what about the other aspect? So wind tunnels are great, but they are just part of the information. And then the idea of power, something that's very, very important. There's an excellent formulation. Do I have anything to write here? I cannot write on anything here. I can write there. Okay, so I guess people might not see it from that who are watching it, but otherwise people would see. There is a calculation that is done. Let's find the one that works. There's a very common thing that we always get, say if you have a Garmin system or you have some other system that you have attached, there's a formulation that looks like this. This is power, this is time. And for every ride, and then for every week, and then for every month, and then for your entire life, you have something of that sort. Let's say that that's 3 hours, and that's 10 seconds. Generally, it is done in a logarithmic scale along the horizontal axis to include more. So that means that that person would be, let's say that's 1,000 watts. That would be a person that for a short distance, short time, can produce 1,000 watts. But for say 3 hours, can produce maybe the average of 20. So you can actually have it, you do it for a lot of people, and then you look at those diagrams, and based on the diagram, you know if this person is a sprinter or a time trialer. Because a sprinter would have something, let's see if I can use another one. Sprinter might have something like that. I'm exaggerating. That in the first few seconds can produce a lot of power and then not very much. A time trialer would be somebody who would have much flatter structure. Cannot produce so much within such a short, in 10 seconds, say, but can keep the power for a couple of hours. So knowing this, you would include that information in the selection that you would say, in case of the home road, we are looking at something where a good rider should do within such and such a time. So for that rider, you would choose what would be that, what that would be.
So even like the two graphs that you have there, how, I assume they're based on like asphalt or a velodrome.
Right, not velodrome, because velodromes are flat,
Oh, yeah.
right?
How much would it change if you do it in like dirt or gravel?
Tremendously. So that would be your change of CRR. You have this coefficient there, CRR, which I think we put 0.05, the measurement on the nice, very nice, smooth, very highly pumped tires. So that would be on the smooth road, and on a gravel would be way more. So you have to do it accordingly, absolutely.
So would it mean you'd have to go at faster speed at a lower gradient?
Say again?
So you have like the critical, you said 12%.
Yes, well, the graph would look very differently. The graph would, I mean, I presume the general shape of the graph would be the same, but the graph could be, say, like this or something quite different. So for the gravel, which, do you ride gravel bikes?
Yeah.
Wonderful, I mean, they're not such a hit in Europe that it's difficult even to, you know, for old guys who want to do the road, we are passé, everybody does just gravel. Just next to my house, there are some gravel courses and people ride them walk. And you would have to just change those parameters, very easy. I mean, it's just you just change your CRR. And then you would do the same graphs, you would plot the same graphs, and then you would use, say, the same argument. You would say that I'm going to roughly choose an uphill where the significant increase or decrease in this case, is moving quite a bit up to that point. From this point on, I don't gain much by increasing the uphill, so I would choose it somewhere here, regardless of what those values would be. The values will change because of the different resistance of the gravel.
Okay.
Where do you ride the gravel bikes here?
Well, I only moved here, but I was looking to do an Everesting on a dirt road.
Oh, you went to Everesting?
I've done one on road.
Really?
Yeah,
And what was your time?
19 hours, 40 minutes.
Nice. And where did you do it?
Back in Ontario.
Okay.
Called Sydenham Road.
How long was your ascent as opposed to, because there's another thing to consider for Everesting, right? How long you want to go up and how long you want to go down?
Yeah, it was about a kilometer and then 100 meters gain per kilometer.
Okay,
It was-
so okay, 10%,
Yeah.
Yeah.
That's the best I could find.
yes.
So I'm trying to think of what percent I should go for a dirt road Everesting.
Yes, I see. So is there such an official thing now as dirt road Everesting?
Yes.
Really?
It's often that.
Cool. Well, if you want, I'm here in Calgary for another 10 days. So we can get together and do some calculations and do that. Very good, very good.
Most immediate application I've seen of the something. Any other questions for our student? Last chance, or yes.
So you might have answered this because of the brand, because I was thinking also about the power, assuming that you have a constant power, but the body, like if I am uphill, the position of the body, the position of the muscles and joints and all of that,
Yes,
I might be more like fatigued when I do it uphill than when I do it downhill. So I need to, in terms of fatigue, I would be tired initially and maybe not be able to keep the level of power that is needed initially.
you mean that you progressively lose the power?
Yeah, exactly, because I need to.
Remember that the constraint mathematically is an average power. That's your average power. So the fact that you might lose some of the power while you're riding, that's still just the average power. But I think that was part of the reason of including the maximum power that you would put in, that you don't want to blow up. And if you go steady, you should be able to do the entire uphill, the entire time trial on the flat also, to maintain the same power. that's part of a strategy that is often, that coaches would often say, especially if you have, say, in North America and in England, it's very common, 40-kilometer time trial, 25 miles. And you should manage your power in a manner that you die the moment you cross the finish line, but not before. That you are steady. If you see somebody that, say, in the last kilometer starts to pick up their pace and sprinting, you say, that's not optimal. Obviously, that person didn't give enough power in the long first portion of the ride. At the same time, if you see somebody, which you do occasionally, after half point, they're basically gone. They started too fast. So that's part, and that's where power meters are very, very important, because I can use a little bit of my knowledge of physiology, which is limited, that power meters will tell you immediately the power that you are giving. You are right away getting the power because it's an instantaneous measure. I even put it somewhere there. The heart rate monitor is not. The heart rate monitor, say if the coach tells you, don't go above 190. Don't go above 190. Well, but if I started and I went up to 190 quickly, then it'll keep on going, because it's not an instantaneous measurement. It's a measurement that if you provoked it to go, then how do I know that I need to stop at 190? If I get to 190, it'll continue. Power is immediate, so it really facilitated a lot. You can see the riders often, sometimes, for instance, Stephen, Kuhn from Switzerland, ran into a banister because he just kept on looking at the power meter. Because that's basically how you ride. You ride looking at the power meter, because that's what you follow, and then you should look ahead at it too. He didn't. He came to the finish line all in blood, so it was, fortunately nothing happened. I mean, nothing very serious. But power meters really made our riding. For the hour record, you are not allowed to have that. You are not allowed to see them. So for coaching, we have the power meters connected to the bike, and the information is stored. But you as a rider don't see it. What you do get, you get your time per lap. And we will make the calculation. So you are supposed to keep, say, 15.4 for every lap, 15 seconds and 0.4. So at every lap you will be told what's your speed, but the power meter is not allowed. It's the rules. Like at some point they can decide it's not allowed to change the bicycle in a time trial. So all the beautiful calculations that we did to change or not to change would cease to be important because the rules would change. But for the time being, you can change the bike. So the rules are such that this makes sense.
All right, with that, let's thank our speaker.